So consider for a second the value of search, how timely and relevant responses bring value to your life. Then consider other Google properties: Mail, Gmail, Chrome, YouTube, Android, and Play. Next, consider that Google delivers these services on a daily basis to 1 billion of our fellow users. And underpinning these services are a set of key innovations and infrastructure that drive them. Our goal at Google Cloud is to share these innovations and infrastructure with you so that you can create value and delight your customers. I'm Babi, and I'm joined by my colleague Oz. And today, we'd like to talk to you about a critical piece of this infrastructure, the Google Global Network. More specifically, we'd like to talk to you about Andromeda. Andromeda is a network virtualization platform for Google Cloud. We'd like to show you how you can use Andromeda to deliver network services that are fast, reliable, and at scale. Before we get started, we'd like to acknowledge the work done by the Andromeda team. More specifically, this presentation is based on their paper that they presented at the Usenet conference for NSDI. It's really a privilege for us to be in front of you and to share the work done by this great team of engineers and many unsung heroes that work tirelessly in terms for delivering these network services day in and day out. How many of you have seen this slide by now, right? But it bears worth repeating, right? We've got 100,000 miles of fiber, both terrestrial as well as submarine, right? It's extremely well provisioned, 20 regions, around 125 plus points of presence, or more than 52 interconnect points, all which gives you connectivity close to where you are, connectivity close to where your customers are, right? And you can get high availability because you can multi-home to any of these 2 regions or 3 regions and get pretty significant availability. Moreover, we've designed this network from the day up for performance and scalability. So we control the point where you onboard on this network. We control the network and the data centers. So at the end of the day, you end up with a very compelling user experience. And we are building this out even more and investing in bringing it out. So I refer to as innovations in networking. The first thing I'd like you to note, and contrary to popular belief, is that we are still innovating in networking. You might have heard Amin Vahdat talk about some of these innovations. What's interesting that he describes is that a lot of these innovations in networking were actually driven by the innovations in distributed services that were powering those services with 1 billion plus users. And he said that those distributed systems required such significant bandwidth that we just could not buy a network that was enough to meet our requirements. So we had to go and build it. And so these are some of the innovations as a result of that. I'll cover some of them in the next slides. But I'd like you to take a moment and notice some of the key commonalities underpinning many of them. Yes, it is software-defined networking. The basic idea between software-defined networking is that you have a centralized control plane that provisions and controls the networking elements for providing connectivity from end to end and enforces policy. You see a lot of those big problems become tractable when you have a logical, centralized brain that takes actually control away from the networking elements, provisions them, and again, enforces policy. Our Andromeda is also based on a software-defined networking architecture. So what does the Google network look like, right? The innovations that I was referring to. Our data center network, Jupyter, it's actually a 40-gig data center clause-based fabric. It's also SDN-based. We have over a petabit per second of total bisectional bandwidth. Connecting these data center fabrics are our WAN network, the B4. It too is an SDN network, and it too has extremely high throughput of the order of terabits. B2 connects our Google to the backbone. It's protected with very high SLAs, and what we do is we try to carry traffic as much over our well-provisioned backbone and well-provisioned network before handing it off to the internet so that your experience is as optimal as possible. Espresso is our SDN to the peering edge. What it does is it actually, with the advantage of SDN, dynamically chooses from where we serve our customers based on end-to-end measurements. So it's not always the most proximate exit point, but because of SDN, we're able to choose what's the most optimal in terms of user experience based on availability and latency. So this is what our Google network looks like. So if you were to take and come and have a piece of Google Cloud, what would some of your requirements be? Some extremely basic. Of course, you need multi-tenancy. You need functional as well as performance isolation. You need it to be highly available. You need elastic network services that help you load balance, protect using firewalls and ACLs, connect to your on-prem, and of course, monitor. You need us to be agile in our feature delivery and iterate and improve and scale and deliver these services to you. Last but not the least, and a key portion of this talk, is that we have to make it scalable. So how do we get there? Before I dive into this question, let me ask you, what thoughts come to your mind when I mention VPC, Virtual Private Cloud? Anyone? Because you see, VPC has different connotations in different contexts. At Google, VPCs are global. It's a global model. It's not isolated. You don't have regional replication of configuration and connectivity. It's also shareable. You can have one policy globally, but you can also have the advantage of fine-grained IAM rules. And of course, on the VPC, we give you access to Google's differentiated services. I'm going to talk about Andromeda in the next section. But essentially, we help you get there to get these network services by running your global VPC on Andromeda. So like I had mentioned, Andromeda is our network virtualization for Google Cloud. What do I mean by network virtualization? It essentially refers to having multiple virtual networks, right, that essentially run on top of a shared physical network. On a virtual network, you can have multiple VMs that essentially talk to each other. And these physical VMs, in turn, run on a physical network. The IP addressing scheme of a virtual network is totally decoupled from a virtual network. Forwarding in virtual networks is done by means of a vSwitch. A vSwitch essentially has a mapping of the destination VM address to the actual physical host's IP address. Packet forwarding happens essentially like it does with all network overlays using encapsulation. You encapsulate the customer's IP packet into another IP packet with the transport header meant for the destination IP address of the host. So now this is where the fun stuff comes. What does the Andromeda architecture look like? The Andromeda architecture is based on a hierarchy of control planes and data planes. At the top of the control plane hierarchy are our virtual machine controllers. These virtual machine controllers receive an abstract representation of the network, specifying what are your QoS rules, what are your firewall rules, what are your routes, what are your subnets, what are the VMs, etc. It then translates that into open flow commands to the virtual switches you see in the gray below. It does not directly communicate with the virtual switches, but it goes through a proxy called the open flow front end. These open flow front ends serve two purposes. One, it serves to decouple the open flow protocol from the Andromeda control plane. It also has no state. It essentially just translates the OpenFlow config commands into OpenFlow protocol commands. Because it has no state, it serves as a static connection point for the vSwitches to the network. Because of that, you can potentially upgrade the control plane without affecting the vSwitches below. The vSwitches have a control plane based on the standards-based OpenFlow vSwitch, but we've added proprietary extensions for delivering some of our network services. Now, a key takeaway from this slide is that our VMC controllers are sharded or partitioned, and that helps you get scalability, right? If you want to bring a new rack online, all you have to do is spin up a new job for a virtual machine controller, some OpenFlow front ends, and voila, you're up and running. Each instance of a VMC is also replicated. There are 3 instances, 1 master, 2 standby, using the Paxos protocol. So having it sharded, having it replicated gives you high availability. So our VMC, essentially, our whole control plane is highly available and does scale out. Now moving on to our data plane. If there's one thing I'd like you to take away of our data plane and what's unique about our data plane is that it is a very performant, OS-bypassed user space architecture running on a dedicated CPU core. When I say fast, even though it's running on user space, we can hit about 3 million packets per second. It's crafted very optimally, taking advantages of things like memory locality, avoiding synchronization like locks, and taking advantage of large page sizes, and avoiding thread handoffs, and avoiding system calls, doing end-to-end batching, all to make it extremely fast. Now, it's also extremely secure. Remember, this is a process running in user space. There is no root access. In addition, the code is so constrained that its attack surface is also very limited. We also implement the best-of-breed security practices, such as address space layout randomization, and having stack canaries, all to prevent stack overflow. So net-net, it's an extremely secure process. One point I should mention is, let's contrast this implementation of the data plane with other alternatives. One thing you could do with the data plane is implement it in a kernel, or you could implement it in hardware. The challenges with those are, if you have a crash in the data plane in a kernel, you take the whole system out. And God help you if you have it in the hardware. Last but not the least, it's also robust. When a process, it's a user space process, so you can restart it. The control plane just detects that the user space has crashed, and you can restart it very easily. In addition, we have mechanisms by which you can do a hitless upgrade of the data plane process. So net-net, we can effectively roll out a data plane change every week, be agile, and have many rapid releases on the data plane. So with this control and unique data plane, what are some of the network services enabled by Andromeda? You, of course, mentioned isolation as your requirement. We'll see some of these services and how Andromeda enables some of these services. But 2 key takeaways are, we make them very highly available, and there is no choke point. It's an architecture that scales out very well. So diving right in, how do you get functional isolation? Functional isolation, it's a standard overlay model where you encapsulate your customer IP packet in the other outer IP packet, and essentially get functional isolation that way. Performance isolation. When I mentioned that the data planes were hierarchical, the control and data planes were hierarchical, even the data plane has the following paths. We have the fast path. This is for your performance critical path. It has fixed cycle budget, and there is isolation by TX and RX for that. In addition, there are certain networking features that are obviously CPU intensive that will take more than necessary cycles than usual. For those, we have the CPU intensive path, and the way we implement them are per VM threads, CPU attributed to the VM container for those more CPU intensive operations. This essentially allows us to be more fair because it's a per VM thread with attributes for that fairly allocated for that container. In addition, having the CPU intensive path helps us to decouple the feature velocity from the fast path. So typically, you're not modifying the fast path when you want to add new features. You typically add new features that are more performance intensive with the per VM thread, so you maintain both feature velocity as well as not disrupt the core fast path functionality. There's also something called Hoverboard. I'll discuss this a little further down the road, but it's essentially a dedicated software gateway for processing the long tail flows. Now, before I kind of gave the answer away, but essentially, how many of you remember the Spectre bug, right? Mind melt. So if you remember, when we hit that bug, we were able to upgrade our infrastructure and just let you guys, our customers, our users know that we had upgraded, that there was an issue, we had upgraded it. And the way we were able to upgrade the infrastructure without disruption was by using live migration. What is live migration? Which is essentially migrate one VM to another machine with extremely minimal blackout period. Where does Andromeda come into the play? Andromeda facilitates live migration even across clusters. If you step back a little bit, right, if you think of a global routing plane and routing converges, enabling us to do, and the time it takes for routing to converge, the time we are able to do this VM migration across clusters is pretty impressive. And like I said, it's useful for maintenance upgrades, optimizing the placement of VMs, and of course, fixing the zero-day bugs under the cover. The way Andromeda does this is it essentially directs the migration source host switch to hairpin all traffic that it receives from other gateways and hosts to the target switch during the blackout period. After the blackout period ends, it then instructs all other VMs and/or gateways to then send traffic to the target switch. So this is this is a very useful feature for us, maintaining high availability and resiliency. Now, going on to the network services that I'm referring to. Internal load balancing, it essentially helps you scale and grow your services behind a virtual load balancing IP address that are only accessible from the backend instances. Inside the Google network, inside your customer network, it's all, it's mostly RFC 1918 addresses. So you use an RFC 1918 VIP for this purpose. We support, we support health checks, and we preserve the client IP. What's important to note is that internal load balancing has no middle proxy. There is nothing called an actual internal load balancer, right? So traditionally, you had a VIP, you had an actual proxy instance that did the load balancing to your backends. But the way GCP does this internal load balancing is that the load balancing functionality is directly embedded and programmed in the client VM itself. So the load balancing decision happens in the client VM itself, and it then gets sent to the appropriate backend. What this means is that we can scale out our load balancer without having any choke points. The way it works is essentially the controllers program the open flow rules into the client VMs. It associates the backend VMs with the VIP. The open flow, there are certain proprietary extensions in terms of doing sticky load balancing, because you have to do both connection tracking as well as doing consistent hashing to essentially get the load balancing function that is both scalable, fair, and also resilient to outages. We support health checks that track the state of the backend instances. And this is essentially what the control plane for an ILB looks like. Now, you have to connect on-prem. Typically, you use either a physical router that has both support for BGP and VPN functionality, and the BGP portion of that gateway learns your on-prem routes, and then the data plane of that gateway encrypts it using IPsec VPN and then sends it across the tunnel. We took a slightly different approach. We could have, of course, just deployed this instance, but in order to make your router both scale and make it highly available, we actually took the routing piece and made it a separate job. A lot of our implementations are essentially just, you can think of it as jobs running in our fabric. This cloud router job peers with the BGP on-prem, learns the routes, and then it programs those routes to the VM, telling them that in order to reach your customer data center, send the packets directly to the VM. So what does this buy you? You essentially get a separation of the control and data plane. Hence, you get more resiliency. When I talk about high availability, what this translates to is that you have essentially VPN jobs or router jobs that are available in a pool. When we have a command to create a VPN or create a router, the config manager essentially instructs, let's say for a router, the routing manager to allocate a router from this pool of router tasks and assigns them to that job. The routing manager then talks to the fabric manager and the Andromeda control plane, setting up the associations between the router and the VMs, right? Now, should a router process crash, it's fine, because the data plane continues to forward packets as before till the BGP hold time. The routing manager, which is tracking the routing instance, detects that the current router has gone away, spins up a new routing instance, and essentially reestablishes a relationship. So you have high availability and no downtime, even if the control plane of the router crashes. Similar fashion, think of firewalls. Typically, firewalls have been deployed at the perimeter. They were potentially choke points, and they didn't scale very well. With Andromeda architecture, our firewall rules are actually deployed directly on our compute engines, the ingress and the egress. There is connection tracking, and that's the way we are able to scale, because there is no choke point. All the firewall rules are deployed directly on the compute engines per se. So to summarize, there is no choke point. It's stateful with connection tracking. And we also support flexible grouping mechanisms for tags and service accounts. So now we've seen services such as firewalls, load balancers, and routers being deployed using Andromeda. I'm going to segue into a new topic, but that's very relevant. How do you scale with Andromeda? Remember when I had made a reference to it being a global network? Well, global networks are big. You also have to remember that a lot of our users are Fortune 100 clients and a lot of large internet companies with very large internet-based workloads. So there are asks for a network having 100K plus VMs, in addition to having more networks. Another point to note is that it's not just the size of the network or the number of networks. There's also the concern of how do you provision a large network really, really fast. So if you take of use cases such as MapReduce or TensorFlow, there is a need to provision a really large network really, really fast. How do you do that? So the way we do that is with using hoverboards. Hoverboards are, in essence, a software gateway. If you come from the routing world, think of it as a top-of-rack switch. I mean, think of it as a route reflector, a BGP route reflector. If you come from the switching world, think of it as a top-of-rack switch, right? Which is essentially forwarding information for all the flows. Of course, it's a dedicated software instance. You can have larger forwarding tables. The virtual switches themselves have essentially, they're a default the hoverboard's a default gateway, default routes from the virtual switch itself to the hoverboard, right? Very standard. So with this way, you can scale your control plane. The reason programming time is not significant because, see, all your programming is a small subset of hoverboards as opposed to programming every switch. As you can see, the order of difference in terms of programming time. Last but not the least, it's important to note that if you're getting control plane scalability, there's a trade-off in data plane scalability because you are having to provision your data plane to deal with the peak bandwidth. You have to provision the hoverboard to deal with that peak bandwidth of all the flows. So how do we get around that requirement for supporting the peak bandwidth of all the flows that has to go through the hoverboard? Well, the way they do it is we essentially offload some high bandwidth flows to the virtual switches directly, right? So we essentially we detect that a flow is very high bandwidth, and we program it directly to go from the virtual switch to the virtual switch itself and offload the hoverboard. In this way, we get both control plane scalability as well as data plane scalability, right? So, but how does this work really? Why does it work? We went and studied all the network flows in our data center, all the east-west flows. And we noticed is that most VM pairs don't really talk to each other, and very few, if they do talk to each other, have very low bandwidth requirements. It's only an extremely small amount that has really high bandwidth flows amongst them. So those are the ones we offload from the hoverboard to the vSwitches themselves, right? Now, going back to just this point about why is it quicker to provision the hoverboards, right? Because you have only a small subset of these software switches that you have to provision, so the programming time, is nice and linear. But think about pre-programming all the virtual switches with all the forwarding rules. It essentially starts out as a quadratic growth in terms of programming time. But slowly, if you are in a specific zone and a lot of VMs share the same physical host, the programming time then becomes linear. But it's too late. I mean, you've already exceeded the programming time with the quadratic growth. So effectively, with hoverboards, we're able to see a 37% improvement in programming time for large networks. We've started implementing routing features on the hoverboard. Additional features such as load balancing and other firewall features are in progress of development. Now, I'm going to hand it over to Oz, who's going to show you a real ILB in action.
In this demo here that we have prepared, the idea is to show you guys a real use case with some of the features that Babi was covering and delivered using Andromeda. So we have an automated deployment with multiple VPC networks, as you guys can see here. So 3 VPC networks, one called DMZ, another one prod, and another one dev. Those VPCs are being connected by multi-NIC Linux firewalls. And in those VPCs, there are also internal load balancers attached to managed instance groups doing AutoScaling. So with this demo here, what we are going to show is the AutoScaler in action, showing the ILB with the preserved client IP that Babi mentioned. So there is no proxy in the middle, so connections from the clients go directly to the servers. We are also going to show the service discovery, the DNS name for the ILB, which is a new feature, and how to monitor all of that with a StackDriver. So here in the beginning, let me just increase this here. So what we are going to show is first the networks being defined. So the 3 networks that I mentioned, dev, prod, and DMZ with different segments. Now defining the firewall rules, which are defined at the VPC level, but enforced at the instance level. So one of the rules, the last one, are the health checks that are required for the ILB. And next, the instances that we have. So we have the bastion that we are going to use for access, the load test VMs to generate traffic, and a single a web server in this first step, just to show you guys the performance that we are going to generate and blast that VM. And so just to show you here, there are 2 MiGs, both of them with AutoScaling off. And the web server MiG, there is just a single instance, AutoScaling off, so it's not going to AutoScale. Next, what we are going to show here is providing access just to show that this is a live environment. So the real IP, for example, for this first Linux firewall is getting through the GCLB and then going to the Linux firewall. So this is the nice landing page. One thing that I just wanted to highlight, it's doing NAT. So that's why you do not see the XFF there, but you do see the real client IP. Now, there is a GCLB configured to deliver this service as well. So the GCLB, the external IP that is providing the load balancing across the firewalls, if we hit it, you guys will see a difference, which is the X4.4 header, because the GCLB is a proxy-based service. So that's the main difference, just to show you guys that both services are, the services are available through both the GCLB and the direct connected IP. Now we are going to connect here to the Bastion host and start basically 2 connections. One to the web server and another one to the load test. So we can generate traffic and show you what a single instance can deliver. One important thing also to note, and I'll highlight here during the demo, is I have 2 web servers loaded. So one of them is showing, responding to port 80, which is the one that you saw there, which is a very, very small page, so low request. And the other one is 8080, which is running a high process. So here, I'm just showing a command, just to show you guys that this VM is programmed to respond to packets destined to the ILB, which is the 10.0.1.10, as you guys can see there. So that's how we can show that the IP, the packets that are delivered to the server, they reach directly the server. They do not flow through any middle layer. Now we are going to show here the servers that I mentioned. So there are 2 servers, one listening on 8080, another one on 80. On 80, it's that simple landing page that I showed. And on 8080, it's actually a fractal. So I'm going to I started here a CPU utilization monitor. As you guys can see, there are pretty much no utilization. And I'll generate some traffic. Since this web server is running a fractal, so there's a lot of CPU utilization. So I'll generate 2 sessions actually, which is here the command. So it'll be 20 sessions with a rate of 2 per second. And so we can see the CPU spiking close to 85%. So, and again, this is using a very CPU-intensive server. So once we do that, we are going now back to the MiG to show, to change the config of the MiG so we can show the auto-scaling. And just before that, if I issue here a command with the watch, so we can take a look at the open connections and generate the sessions again, then we are going to see that the commands targeting now the ILB will be so the first is targeting the real IP, right? So the IP from 0.5 targeting the .6. The next one that is going to be done here is generating traffic targeting the ILB address, which is this DNS here being highlighted. So that's the DNS entry that was created, was defined when creating the ILB. So sending packets to that ILB, then we can see that actually the packet monitor will be done here in the next. So first a curl, just to make sure that that ILB is responding to the traffic. And now when I start generating that traffic, then we'll be able to see in the connection tracking that the target IP is 10.0.1.10, which is the ILB. So that VM, once it's part of a managed instance group tied to the internal load balancing, is programmed to respond to packets destined directly to the ILB. And one thing to highlight here is that the number of sessions, which was around 2,000 connections per second, was the same number either targeting directly the web server or targeting the ILB. So there is no choke point in the middle. So now we are going to configure the instance group and increase the max size, actually enable the autoscaler. So we go to the MiG, edit the managed instance group, enable autoscaling, and set the target CPU utilization to 80%, increase the number of instances to 6, and reduce the cooldown. So cooldown period is the number of seconds before the instance is seen as ready to receive traffic. So we're going to change that just so it improves our demo. But in real life, you should monitor that and see the amount of time that you need before your instance is ready to receive traffic. Now, I have started the CPU utilization. Just to show here that it was changed already, so it's ready to receive traffic. And if you take a look at the monitoring in the console, we can see that there is one instance, and the total CPU usage will be available will take a few seconds, but will be available as 80%, which is the threshold that we have set. Once I start generating the traffic, which is here, so 1,200 sessions, with a rate of 4 per second, then I'll blast the CPU for this machine, and we'll have to wait a little bit until the MiG kicks in. So now, switching to StackDriver, I have created this custom dashboard that will show the per VM CPU utilization plus all the ILB statistics, so we can monitor. But also, if we go here directly to the instances, we can see a list of all the instances that's going to load here with a CPU utilization. Now we are seeing just one, because of course it takes a few seconds until the MiG kicks in, the new instances are created, and the CPU is loaded. We can also see this new feature. I don't know if you guys are aware, but in StackDriver we have loaded several metrics and available already in StackDriver for the ILB. So we can see all the throughput, the packets, inbound, outbound, latency, for doing a breakdown by instance group, for example, by server, or showing all the key metrics here. So it's everything available already in StackDriver. This is built in. There's nothing that needs to be customized to see this. And then you can break down by several parameters here, several options, and then take a look at it. Similarly, just to show you guys here, we also have metrics available for GCLB. It's not the focus of this presentation. We have others specifically covering the Google Cloud Load Balancer. But so you guys see, there's several metrics already built into StackDriver to allow monitoring. Now, what I have done is build a custom dashboard to monitor all my main servers. So I'm grouping all servers named by prod MiG, and also all the ILB related statistics. So we can see here that the one VM that the StackDriver is seeing already has a spike here on CPU, has a high CPU utilization. So once we go back now to the console, we can take a look and see if the status of the MiG and if it's increasing already. Yep. So doing a reload, then we can see here that not yet, but the members are actually being spun up. So just one thing, the VMs are being spun up. Soon they will be ready after the cooldown period, after those 15 seconds, and they will be ready to receive traffic. So once they are ready to receive traffic, after it's up and running in those 15 seconds, the VM is reported as running. And after those 15 seconds, they're configurable. Then we are going to see the traffic being loaded, distributed to all the VMs, and we'll see the VM utilization for this first one being reduced. So it will be distributed. So it takes a few seconds. So also, so you guys know the MiG is pretty quick to kick in. However, it takes into account the last 10 minutes of VM utilization to take decision to scale up or scale down. So that's why it takes a few minutes to actually make the decision. But now you guys can see, so it has increased already to 240%, I believe, to 3 CPUs. So if we reload here, we'll be able to see the CPU information and utilization. So the VMs are already loaded here and available with the CPU utilization soon. And now back to the GCP console. Once we refresh, we are going to see this utilization growing to actually 480%, which would be the 6 VMs that I have configured times 80% of available CPU utilization. So well, here in this demo, I'm using the CPU as a metric to provide the auto-scaling, but you could also use, for example, custom StackDriver metrics to do this auto-scaling. So StackDriver supports custom metrics you can build on your own. You can install agents on your servers to monitor the parameters that are more important for you. And then scale up based on that, scale up and scale down. So now as you can see here, we can see all the VMs ready and utilization of 200% out of 240%, which are 3 VMs times 80. And now we see that the CPU utilization in the first VM is reduced because now the traffic is being spread across more VMs. So we'll do some refresh here. So to see the updated information. Now, I think in the next one, all the VMs will be ready, and we'll see 480% CPU utilization available that could be used. We'll then do I will do a fast forward, just because it takes 10 minutes, taking into account the last 10 minutes to scale down. So you guys can see that after traffic is stabilized, I stop generating traffic here. Then we'll see the utilization going down again, and then scaling down the servers and back to normal life. So, and just to show you here what would look like in StackDriver. So in StackDriver, it takes a few seconds to get that information and load in the graph. So it's starting to load here and create a nice graph for you of all the CPU utilization and the data. Yeah, so now the capacity is 480% and reduced to 120% utilization average. So one thing that is important, this CPU utilization that we configure here is an average. It's not a total per CPU, but an average calculated of all the CPUs. And now going back to my to my dashboard, my custom dashboard. So I have all the CPUs now added here with utilization on a per CPU basis, so it can be monitored and all the data. And you can also set the alerts here from StackDriver. So now back to the MiG, we can see all the MiGs, all the servers were created. One thing that I would like to highlight here is that I'm using a regional MiG. So as you guys can see, there are 2 instances per zone, 2 in Central B, 2 in Central 1C. So you're providing zonal redundancy as well. So traffic is being distributed in the same region across multiple zones. Then now that's the fast forward that I mentioned. If we go back and check now on the details, the auto scaling is on, but the number of instances is 1. And then the scale down over time at the course of those 10 minutes, it's going to decrease the utilization and then scales down back to one VM, as you guys can see there in the graph. Now, so back to Babi.
So what this means for you, remember the global network. We support resiliency with live migration, and we support scale and performance, right? We hope we've shown you some aspects of the Andromeda architecture, how it allows your network services to scale, to reliable, and they're really fast. One more thing. We're just announcing in alpha support for 32 gigabit networking. Of course, you need the Skylake CPU platform, but you don't need custom drivers, and you need 16 vCPU or higher. So these are some of our GCP networking sessions that I'd like you to check out upcoming, and of course, you can check them out, the Encore versions, on YouTube. In addition, if you would like a cloud poster, a 36-inch by 50-inch showing the Google's global network, please sign up, and then you'll get one free shipped to you in the continental US.